Okay, so this is my 98th attempt to record this video. I'm getting really quite disappointed with it. But I really wanted to explain to you why we need the C cubed in this. A couple of you asked about it. It's a really good question. And it's also a great technique for solving this problem, which didn't occur to me. So yeah, let's do it. So you've got to show that, well, actually in the question, it turns out that there isn't a value of k for which this is a cube number. And I wanted to show you sort of like a general approach you could use for trying to find a value of k for which a cubic polynomial is a cube number. Now, we know we can factorize it into that. And the question basically is why can't we just let this be k plus 1 squared? Why do we need a c cubed as well? Well, it's a really good and subtle point. It's actually because, think of something like this. Can you see 2 times 2 squared times 3 cubed? That's a cube number because it's 2 cubed times 3 cubed, which is 6 cubed, which is 216. It's for this particular situation. Consider this. Here's a polynomial, and I promise you when k is 3, it equals 216. You can factorize it like that, but if you were to let that equal k minus 1 squared, because I've specifically engineered it so, you end up with k equals minus 4. Now, that doesn't make any sense because k is supposed to be a positive integer according to the restrictions in the question. Now, what went wrong? Because k equals 3 does give 216. Well, we're missing a c cubed here. Now, this is the way you'll handle a c cubed, just to show you how you'll handle the question after introducing the c cubed. This is what I did anyway. I did, okay, so c cubed equals that divided by that. Sorry, it's so annoying using a Windows computer. But okay, so that divided by that is c cubed. You can do a bit of a jiggery pokery with the first term. This is standard kind of like way of like doing kind of partial fractions very quickly, but we can make this into 1 minus, or long if you like, k over k squared plus 2k plus 1, and get a contradiction because the only cube number which equals 1 minus a positive integer is 1, and if c cubed is 1, k is 0, k is supposed to be a positive integer, hence you can't do that. Yeah, hence you can't do that. Now, if we were to use the same approach on this sort of engineered polynomial where there is a cube number, we would let this equal k minus 1 squared times c cubed. Now, I can't write on my computer because I'm on holiday at the moment, so I've had to do it all kind of like with LaTeX, and it's quite hard to do. But try solving this now with a times c cubed on the end, and you'll end up with this basically a 1 plus a value, and that then there's no contradiction. You'll find that k equals 3 nicely gives a cube number of, I think, c equals 3, and therefore c cubed is 27. But yeah, give it a try, see what you think, and hopefully that's cleared that up. But it's because essentially the reason why you need the c cubed is because you're thinking just that all cube numbers are like I don't know, take something like 125, 5 times 5 squared, a prime number times a prime number squared. But that's not necessarily the case. You can have most cubes, actually, cubes of any composite number will have this quality, and it will fail unless you include a times c cubed. So, look at my example of when it fails and have a good think about it, and hopefully that will clear things up for you. But yeah, thanks for listening, and I hope it was useful, and all the best. I won't be recording actually until for another just over a week, and then I'll put some more videos up. I'm doing lots of these questions on holiday, but I just cannot suffer the laptop that I'm using. It's just useless for this kind of thing. Okay, thanks for listening, and bye bye.